Hello students and welcome to the lecture on Perceptron Learning Rule. Perceptron Learning Rule, the 12th lecture in the lecture series for the course of Artificial Neural Networks for Electronics and Telecommunication Engineering students of the 7th semester, Goa College of Engineering. I am Ms. Purti Savardekar, the faculty in charge for this course. Perceptron sounds like a machine character from the movie Transformers, isn't it? It is so because it was actually intended to be a machine rather than a program. It was called Mark I Perceptron. The machine was designed for image recognition. It had an array of 400 photocells randomly connected to the neurons. Weights were encoded in potentiometers. Weight updates during learning were performed by electric motors. The Perceptron algorithm was invented in 1958 at the Cornell Aeronautic Laboratory by Frank Rosenblatt, funded by the United States Office for Naval Research. Frank Rosenblatt was an American psychologist notable in the field of artificial intelligence. Although the perceptron initially seemed very promising, it was quickly proved that perceptrons were capable of learning only linearly separable patterns. More nodes can create more dividing lines, but those lines must somehow be combined to form a more complex classification. A second layer of perceptrons is required. That is then sufficient to solve many otherwise non-separable problems, like the XOR problem. Does this ring a bell? We have studied this before. Yes, it means that perceptron learning rule is used for neurons with binary response, a TLU, threshold logic unit. We have solved problems in this manner. But at that time, we visually chose the hyperplanes to obtain the weights. Today, we will learn how to train the neuron to achieve those weights using the perceptron learning rule. Because it is a learning rule, the perceptron learning rule also provides change in the weights as the output. But what is the mathematical expression that gives us the weights, the weight updates? Perceptron learning rule is the simplest supervised learning rule. Supervised, that means a desired output is given in the training set along with the input. The training set is given as input and the desired output, a pair of input and desired output, input-output pair. To understand the perceptron learning rule better, let us consider this neuron model. This is the ith neuron. Its input x is written as xj because it is the output coming from the jth previous neuron. The weight between the jth presynaptic neuron and the ith postsynaptic neuron is written as wij. Yes, wij. The output of the ith neuron is given as f of net I. In perceptron learning rule, when a certain input is given to the neuron, the output of the neuron has to be compared with the desired output. This comparison shows how different the neural output is from the desired value. Our aim is to make sure that the neural output becomes equal to the desired output. Our aim is to make the difference between neural output and the desired output 0. If the difference is not 0, the difference has a value. That means the neuron has to learn. The weights need to be updated. That means the weight change is proportional to the difference between the desired output and the neural output. This helps us with the mathematical equation for weight update. For a particular training pattern, the weight update rule is given as delta Wij equals C into Di minus Oi into Xj, where delta Wij is the weight between the jth and the ith neuron, C is the learning constant, Di is the desired output, and Oi is the neural output for that training pattern. This is the same as delta Wij equals C into bracket Di minus f of Wi transpose X, bracket complete, into Xj. Here capital W transpose capital X is the product of the entire weight matrix of the neuron and the input pattern matrix. Note that the perceptron learning rule is applicable to only binary neurons, that is the signum activation function. Therefore, we can write this expression as delta Wij equals C into bracket Di minus signum Wi transpose X, bracket complete, Xj. And that is the mathematical equation for the perceptron learning rule. Let us now expand this to a neuron having multiple inputs, as is usually the case. Let us consider this neuron. This neuron has capital J number of inputs and corresponding weights and one output. How do we calculate the correction for the entire weight matrix? Entire delta capital Wi? Following the same equation as before and then further expanding it, we obtain delta capital Wi equals C into Di minus signum Wi transpose X, bracket complete, into capital X. This is how we find the entire weight matrix using the perceptron learning rule. Let us now discuss some implications of the signum activation function and hence the working of this perceptron learning rule. If we assume a binary bipolar activation function with possible neural and desired outputs either +1 or -1, then Di and signum Wi transpose X can have 4 combinations as shown in this table: +1 and +1, +1 and -1, -1 and +1, -1 and -1. The difference then obviously becomes 0 for the cases where desired output and the neural output is the same. It matches. That means the weights are correct and are generating the required outputs. No change is necessary. Therefore, delta W is a 0 matrix. Now consider this case where the desired output is +1 and the neural output is -1. The neural response needs to increase. It needs to go from -1 to +1. According to the correction that we obtain, it makes sense that it is equal to +2cx. We add a fraction of the pattern to the weight vector. We add a fraction of the pattern to the weight vector. Now consider this case where the desired output is -1 and the neural output is +1. The neural response needs to reduce. It needs to go from +1 to -1. According to the correction that we obtain, it makes sense that it is equal to -2cx. We subtract a fraction of the pattern from the weight vector. Why I am saying it as a fraction is because C value is usually 0.1, 0.2 and so on, in between 0 and 1. That's why this 2cx becomes a fraction. So here we subtract a fraction of the pattern from the weight vector. Pause the video for a minute or two and go through the table to establish a certain your understanding. To understand the algorithm better, let us try to solve an example problem. The problem statement is: consider the initial weight matrix W1 equals 1, minus 1, 0, 0.5. The learning constant C equal to 0.1. The training set having the input patterns x1 equal to 1, minus 2, 0, minus 1 with D1 equals minus 1. This is the input output pair. X2 equals 0, 1.5 minus 0.5 minus 1 with D2 equal to minus 1. And X3 equals minus 1, 1, 0.5 minus 1 with D3 equal to 1. And bipolar signum neurons. Perform one iteration of the training using perceptron learning rule. Our current neuron looks like this. So first we consider the training using the first input vector x1. We find the net value using the current given weight matrix like this. Then for this net value we find the f of net value. Now we calculate the new weight matrix like this. It is equal to the old weight vector plus the delta w. Delta w is given by C into D minus f of net into x. We substitute all the values and get this as the new vector. Note that the superscript increments every time the weight matrix gets updated. Now consider the second training pattern x2 and the desired output d2. We again consider the net value using the updated weights. Then the f of net value, and then we find the new weight matrix. Then we consider the third training pattern x3. We find the net, the f of net and the new weight vector. At the end of one entire iteration of training, the updated weight vector should be w4. Take some time and try to obtain w4. I hope that the concepts that were covered in this video are clear. Let us discuss this further in the live Google Meet. See you there. Thank you.